Welcome back. This is the third lesson recording for IM1 for September 25th, 2020. Okay, so we've just looked at the patterns of 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on to figure out what 2 to the power of 0 means and what 2 to the power of -1 and 2 to the power of -2 is. But let's generalize this so that we can apply to not just when the base is 2, but when the base is any number. To do this, I am going to go back to the graphic organizer that you should have, and we're going to fill in the last two boxes. Okay, let's start with the very bottom one, the zero exponent rule, and we'll come back to the negative exponent rule. So when you see this x to the power of 3, okay, we're going to solve this in two different ways. Two different ways that we already know. We're going to first solve this by expanding. If we expand x to the power of 3, that's just multiplying x to the power x times 2. That's the numerator. And x to the power of 3 is also, and the denominator is x times x times x. Okay? And from here, you should be able to see that, oh, I can make my giant ones. Here's my giant ones. Okay? These cancels out to be 1 times 1 times 1. Okay? And what is 1 times 1 times 1? That's just 1. 1 times 1 times 1 is just 1. Okay? Let's approach it a slightly different way. And we have just learned the quotient rule. And that's something that you've been doing from last lesson. Quotient rule tells me that if you are dividing some exponent expression by another exponent expression and they have the same base, x and x, they're the same, in that case you can subtract the numerator exponent, that's 3, take away the denominator exponent, that's 3 again. So the first 3 is from the numerator exponent, the second 3 is from the denominator exponent. Okay, then what does this become? What is 3 minus 3? That's just 0, isn't it? Okay, so that becomes x to the power of 0 is 1. And the reason we are using x is because the x can be anything. It could be 2, as we figured out from the pattern here, or you could be -5, it could be -135, it could be 123.5, or it could be any number. That is the beauty of using variables. That tells us it doesn't matter what it is, whenever you raise it to the power of 0, it's going to be 1. So let me summarize that here. X raised to 0, doesn't matter what it is, any number raised to the power of 0 is going to be 1. Then let's do some examples. What is y to the power of 0? Anything raised to the power of 0 is 1. What's 6 raised to the power of 0? That's just going to be 1. Okay, what about this? I have this really complicated thing here, raised to the power of 0. Well, this complicated thing, it doesn't really matter. It's still being raised to 0, so that's still 1. Okay, now so that was called zero exponent rule. Let's look at the negative exponent rule. And again, let's approach it by this problem by solving it two different ways. One way, we're going to expanding. And when you're expanding x squared divided by x to the power of 4, let's just expand. That just becomes x times x divided by x times x times x times x. Okay? But again, we can create our giant one. But this time, what we have left over is some x's as the denominator, as the bottom numbers in the fraction. So that is just same as the numerator just cancels out to be 1. And you have x times x is just x squared as a denominator. Let's try solving this using the same problem using the quotient rule. Okay, again, using the quotient rule tells me if you are dividing some exponent expression by another exponent expression, when the bases are the same, you just need to subtract the bottom number exponent, the numerator exponent, from the numerator exponent. So this just simplifies to x to the power of, what is the numerator exponent? That's 2. And then from that we need to subtract, what's the denominator's exponent? That's 4. Okay, now we simplify that becomes x to the power of 2 minus 4 is -2. So now we come to the conclusion that x to the power of -2 is really same as 1 over x squared, because we started off with the same expression. We just solved it 2 different ways, and therefore if we start off with the same thing, then we can conclude that we're still going to be ending up with the same thing. So to generalize this, not just for when the exponent is 2 or -2, we can say that x to the power of -m, and m can be any number, is going to be 1 over x to the power of m. And the way you get rid of this negative exponent is just putting it as 1 over, turning it into a fraction. The base stays the same, but everything occurs as a denominator with the exponent number right there. Okay, so then let's try doing some examples. To use that, x to the power of -3 means it's same as, to get rid of this negative symbol, I'm going to put it as 1 over. And the rest stays the same. X and the 3 stays the same, so it's just x to the power of 3. And this occurs as a denominator, or the bottom number in the fraction. And 4 to the power of -2 is 1 over. This negative sign in the exponent tells me that I want to have it as 1 over. You have to turn it into a fraction. And the number, the base is 4, and the exponent is 2 this time. All right, then number 3 is a little bit more complicated. So it's -4 times x. So when you see this, the best thing you should do is separate it first. -4 is being multiplied by x to the power of 5, is being multiplied by y to the power of -2, so that you know which is which. Okay, so -4 is being multiplied by x to the power of 5. Well, -4 multiplied by x to the power of 5, we can't do much with that. But what about y to the power of -2? Well, I have a negative exponent here. I can rewrite this without the negative exponent as 1 over y squared. So y squared occurs as a denominator, and you're multiplying across. Remember, when you're multiplying fractions, anything just becomes anything over 1, because anything over 1 is the same thing. When you're multiplying fractions, you always multiply across like so, and then multiply across like so. So that becomes -4 times x to the power of 5 times 1 is same as -4 x to the power of 5 divided by, the denominator becomes 1 times 1 times y squared is just y squared. And that's your final answer. Okay, so now it's time for you to apply what we just learned and solve this problem. So please pause the video, copy these questions down, and see if you can solve it yourself. And I'm going to go through the answers in 3, 2, 1. Okay, so when you see 6p times 2p to the power of -3, you can do it different ways, but I'm just going to do it one way. First thing you should do is you should bring all the numbers together. Okay, so you're multiplying 6 and 2, and then bring all the p's together. You're multiplying p times, and then p to the power of -3. Okay, now of course, when you see a p by itself, this is really same as saying p is being multiplied to itself 1 time. So I can actually even add 1 right at the top here, because that's exactly the same as 1, p. Then this simplifies to 6 times 2 is 12. Now using our power rule, when the bases are the same and we're multiplying, you just need to add the 2 exponents, right? So it's multiplying by p to the power of 1 plus negative 3. So what? That 1 plus negative 3 as the exponent. Okay? Then that just becomes 12 times p to the power of, what's 1 plus negative 3? That's same as 1 minus 3. 1 minus 3 is negative 2. Now, we do not want to leave our answer with a negative exponent, okay? And the homework will ask you to not to leave your answer with a negative exponent. You want to convert that into positive exponent by turning that as a denominator in a fraction. So I know that this is same as 12 multiplied by, what's p to the power of negative 2? Again, to get rid of this negative sign, I need to put it as 1 over. And this is p to the power of 2. Okay? And again, when you're multiplying something to a fraction, you can always change the number you're multiplying as 12 over 1. And when you're multiplying, you know that multiplying fractions, you always multiply across, like so. So that becomes 12 times 1 is 12. And the denominator is 1 times p squared is just p squared. Good. Okay, now let's go to the next one. Now you have parenthesis 2x to the power of 0 all raised to the power of 2. Okay, now notice that this is not saying 2x all raised to the power of 0. It's only x is being raised to the power of 0. 2 is being raised to the power of 1 actually. Okay, so you can't get that confused. And let's see if we can simplify what's inside the parenthesis first. If you can, that is the goal. Always try to simplify inside the parenthesis. Now we can't do much about 2, but can we simplify what's x to the power of 0? That's just 1. And the operation between 2 and x to the power of 0 is just 1. So that just becomes 2 times, we still haven't done the square, so I do need to still rewrite it. 2 times 1 is just 2, and still need to be raised to the power of 2. So that's going to be 2 squared, which is same as 4. So that's my final answer. And then let's try this problem. Okay. Alright, so then when you have m to the power of 3 multiply m squared, all raised to the power of negative 1. Again, we have this negative 1. Few ways to apply this. Okay, so what I know is, I know according to power rule, when something is being raised to a power and then raised to yet another power, and that is what it's doing, then we can actually just multiply this out, right? So this just becomes m to the power of 3 multiplied by m to the power of 2 times negative 1 is just negative 2. Okay, and now in this case, we can use the product rule and say that m to the power of 3 multiply m to the power of negative 2. Since the bases are the same, this is same as just adding the exponents, so that becomes 3 plus negative 2. Okay, what is m to the power of 3 plus negative 2? That's same as 3 minus 2. That's same as 3 minus 2 is just 1. So the final answer is just 1. Okay, see how much this just became m. It just looked so much more simple. Alright, then I am going to close this, and I want you to try this problem. Okay, pause the video and try this problem now, please. Okay, in the interest of time, I've solved all the problems for you to check your answers. So please look at these answers, pause the video, and see if you agree with this. Okay, and that's it for today.